Yes, starting with this. Hello, everyone. Good afternoon, and welcome to this special asset Vigyan Vidushi combined colloquium. And it's going to be a wonderful talk. And this is also a Vivamir Chaudhary Memorial Lecture. And I request Professor Vandana to come and initiate the proceedings and also introduce the speaker.
No, I'll give the slides. Yeah. So, thank you, Parag, and good evening. Welcome to this special asset joint lecture organized by Asset and Vigyan Vidushi. As you know, Vigyan Vidushi is a summer program started by TIFR in 2020 for women students who are completing their MSc first year and are on the verge of making the career choice. Today's lecture is Bibha Chaudhary Memorial Lecture. So let me just take a minute to introduce Bibha Chaudhary to you. Many of you may know about her. She was the first woman particle physicist in India. If you look at her brief trajectory, she did her MSc in University of Calcutta in 1936. She was only woman in the class. Remember, we are now talking about almost 100 years back. During 1938 to 1944, she worked with D.M. Bose at Bose Institute, where she developed a method to determine the moment of charged particles by observation of tracks in the photographic emulsion plates. 1945 to 49, she worked on extensive air showers in cosmic rays for PhD at Cosmic Ray Research Laboratory of PMS Blackett at University of Manchester. 49 to 53, she was in TIFR. She's the first woman scientist at TIFR. She built the bubble chamber and detector setup for air shower studies. 1961 to 76, she was at PRL. She was also the first woman scientist at PRL, where she worked on cosmic ray air shower experiments. And after her retirement from PRL, 1976 to 91, she continued working in Kolkata on understanding nucleus-nucleus interactions at relativistic energies. And she passed away in 91, so she was passionately working in physics till the end of her life. Her major scientific contributions are actually briefly listed here. As I said, she carried out a pioneering study working with D.M. Bose, where identifying a cosmic particle having mass close to 200 times that of the electron, which is now as we know as ion, which is by exposing photographic emulsion at high altitudes. She published 4 papers in Nature. Some of you who would know it's a very prestigious journal. And the technique developed by them paved the way for discovery of pi meson by Professor Powell, for which he got a Nobel Prize in 1950. It should be mentioned that he acknowledged Bose and Chaudhary's pioneering contribution later in 1959. So this, just to give you a brief view of honors and accolades for her. So a book titled Jewel Unearthed Bibha Chaudhary by 2 leading science historians was brought out in around 2018, and Indian edition of this biography is published by TIFR and TAA, and all the VV participants have received a copy of this book along with their registration kit. It's a very inspirational story. In addition to that, the 2 posthumous honors have been bestowed on her recently. In 2018, the International Astronomical Union named the yellow-white dwarf star as Bibha, and in 2020, Government of India declared a chair professorship in her name to be instituted in TIFR or PRL. Some quotes about her work, as you see from the authors who wrote her biography. Bibha Chaudhary belongs to the first generation of women scientists who began their research career in pre-independent India. Born more than 100 years ago, opting for a research career in physics, visiting England for further research, and working in 2 premier research institutes after return to India were no small feats to accomplish. She did her experiments at high altitudes, Darjeeling, India, and also in Alps, and also in deep mine under challenging conditions. Throughout her life, she remained unfazed by all inattention, immersed in the pursuit of science. And this memorial lecture is a token tribute to her. Her life story is exemplary and inspirational to younger generations. So we hope more and more people learn about it. So we have today's lecture, Bibha Chaudhary lecture, given by Professor Shobhana Narasimhan. Professor Shobhana Narasimhan has a very close association with TIFR. She grew up in TIFR premises. Her father was a famous mathematician, was working at TIFR. She also has even closer reaction because she was like you are doing a summer school. She actually did a summer project here. She was a VSRP in TIFR in 1984. Yeah. She did her MSc at IIT Bombay and then did her PhD at Harvard University. After postdocs at Brookhaven and Fritz Haber Institute in Berlin, Germany, she joined the faculty of Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore in 1996, where she still continues to work as a professor in theoretical science unit. She is a fellow of American Physical Society, American Academy of Arts and Science, Indian Academy of Sciences, and National Academy of Sciences in India. In addition to her research in computational nanoscience, about which you will hear from her shortly, she has a strong interest in promoting the cause of women in science and in teaching physics in developing countries. We are very happy to have her here because in the first edition of Vigyan Vidushi in 2020, she gave a special lecture, but that was online, and there she talks about, in general, the women in science in India, and that, of course, is available to you. But we are very happy to have this opportunity for our participants to interact with you and to learn from.
What is it on? Mic, you can hear, right? Okay. Thank you, Vandana, for inviting me to give the Bibha Chaudhary Memorial Lecture and also to address Vigyan Vidushi, which is a program close to my heart. So today I'm going to talk about why do computation. So I have organized my talk in 3 parts. So first I'll tell you a little bit about myself, then about computation, and something called density functional theory, which is the field I work in. And then I'll tell you some examples of work from my group. So, I have to put my timer on so that I can pace myself. Sorry. Just a second. Okay. So, I'll tell you now a bit about myself. Vandana already told you a little bit about myself, and I might repeat some of that. But given that this is a talk for women students, I thought I'd start by telling you a little bit about my maternal lineage. So that is my great-grandmother, Lakshmi, whom I have seen once as a child, because if you see, she died a year after I was born. She was married at the age of 8. In those days, that was common, but usually you didn't go to your husband's house until you achieved puberty. But in her case, her mother-in-law was very keen that she didn't have any daughters, so she wanted Lakshmi to move to her house. So at the age of 8, she was married and sent to her husband's house. She didn't want to get married. She was running around and playing. And her mother-in-law said to her, "If you come and sit here, I will give you a mango." So she went and sat, and then she got married. Okay. And she was a very good musician. And she wrote many musical compositions. She didn't get much time for this because she was kept busy with housework, etc. But as you know, in those days, and still to some extent nowadays also, women are kept aside for a few days of the month when they have their period in some families. And so those were the only days of rest she got. And it was during those days that she wrote these musical compositions, which have now been handed down in our family. Next, you have my grandmother, Sugandha. So she studied up to high school, and then she got married at the age of 18, which was considered shockingly late in those days. She, however, after getting married, went on to study BA and an MA by correspondence. She was also a very well-known musician, and she later set up a school of music. Then you have my mother, Shakuntala, who got married at the then shocking age of 23. And she was doing her PhD in economics when she got married. And sadly, she couldn't complete that PhD because a year after she got married, I was born. And then with the responsibilities of motherhood, etc., she was unable to complete her PhD. And she was also a very good singer, is a very good singer, but she completely lost her voice. Like when I was early memories are of her whispering to me because she'd lost her voice. Doctors couldn't figure out why she'd lost her voice. And then she was very frustrated sitting at home, not able to do a PhD, not able to sing. So she started writing. And because that's something she could do from home. And she went on to become a very well-known writer and journalist. She won, for example, these really prestigious awards for journalism. And after I got my PhD, I told her, Amma, now I've got my PhD, it's your turn. You go and do your PhD now. And she did do her PhD. So she now has a PhD. And then, of course, there's me. And I didn't get married. I have a PhD, and you can learn more about me through the course of this talk. I'll also tell you a little bit about my father. As you have heard, he was a mathematician who spent most of his career at TIFR. On this first picture, oops, what was that? This person here, this little kid with the shaved head, with the kurumi, if you know what a kurumi is, it's this top knot here. He had diamond earrings in his ears. That's my father. He grew up in a very small village in Tamil Nadu, where there wasn't even a high school. His father died when my father was 12, and then the family had severe financial difficulties. But my father just loved books and loved maths, two loves that's continued throughout his life. And he went on to become an internationally renowned mathematician. And the middle picture is me with my father. And what I put, the two tweets are there. One is a post from Ed Witten. I don't know how many of you know. How many of you know who Ed Witten is? Okay, very few. So Ed Witten is possibly the most famous physicist in the world. He's in Princeton at the Institute for Advanced Study. He's a string theorist. This is him tweeting about my father passing away 3 years ago. And the bottom tweet is from Narendra Modi, also tweeting about my father passing away. So obviously, I was influenced a lot by both my parents. And I grew up just a few hundred meters from where we are today. I think the first professional talk I gave was as a summer student in this room. And I was horribly nervous because usually like 10 people would come and listen to a summer student's talk. But because everybody knew my father, the room was just full. And I hated it. I was so nervous. So my academic trajectory, I started out in what was then called Bombay. I went to school, college in IIT Bombay. And I didn't like physics, okay? I first started learning physics in the 8th standard. I would never have dreamt that I would become a physicist. It was one of my least favorite subjects. Then after IIT, I went to Harvard for my PhD. Then I went for a first postdoc at Brookhaven, a second postdoc in Berlin. Then I came to the Jawaharlal Nehru Center for Advanced Scientific Research, which is in Bangalore, where I still work. So these are some pictures of JNC. And we've been given instructions that whenever we give a talk outside JNC, we have to boast a little about JNC. So I'm going to do that now. Okay. So in 2019, Nature, I think you all hopefully know about Nature. It's a very prestigious scientific journal. It ranked institutions worldwide, but normalized by their size, that is taking account for the fact that a smaller institution will have fewer publications, etc. And JNC came 7th. Okay, and if you look, you will see Princeton University is 10th, Stanford is 11th, MIT is 12th, etc. So this was something we were obviously very delighted by and was also quite unexpected. We didn't realize we were that good. Okay, so this is my group of students. One student who joined recently is not in this picture. Now, I want you to look at this student, Garima, and I will tell you a little bit about her. So, how did Garima find out about me? She found out about me through Vigyan Vidushi 4 years ago. That was in the middle of the pandemic, and so it was held online. And here is a screenshot taken at the end of the program, and that's Garima, and that's me. Okay? And then Garima's story also, I think, is quite interesting because she told me that after she did her BSc or 12th, I don't know, she had 2 career choices to make. I mean, she could have done fashion design or she could have done physics. So she also got into this fashion institute, I forget what it's called in Delhi, very prestigious. And she got, I think, into St. Stephen's for physics. And she had to really think hard which one she wanted to take because she liked both these things. And then she finally chose physics. So she's now doing her PhD. The topic of her PhD is materials for qubits. So this is a new field in our group. So she and I are learning the topic together as we go along. And I put some pictures here. So she and I traveled to Europe together last year. For the first pictures of us in Munich. And the second 2 pictures are of her at an interesting workshop that was held in Trieste in Italy, which is a workshop for women in physics, which I've been organizing for many years now. And the middle pictures of her doing a presentation there, and the last pictures of her with women from around the world at this workshop. Okay, so she conducted a couple of sessions at this workshop also. So I do have a strong interest in mentoring women in science and supporting women in science. So for many years, 11 years now, I've been conducting these workshops for women in physics. They've been held either in Trieste in Italy, or we had one in Kigali in Rwanda. We were supposed to do one in Bangalore, but it was unfortunately scheduled for 2020, and then we had to cancel it because of the pandemic. And the bottom picture is one thing I do rather often is I go to Africa and teach in various countries, teach physics and density functional theory. And the bottom picture is of me with 2 of the students I taught, Anne Justine from Cameroon and Winnie from Kenya, and they're both now faculty members in their countries. So what do I enjoy besides physics? Okay, I have lots and lots of interests besides physics. They're still a bit geeky and nerdy, but I like doing many things. I like reading, I like writing, I like cooking, I like baking, I like to solve crosswords, I like to set crosswords, I like to travel. This first picture is of a crossword we recently set. This picture is of me with some of my students in Paris. And in case you're wondering why I'm doing this weird thing, I have this joke that my students are always like little birds, because whenever I travel and come back, I feel they're like with their mouths wide open saying, feed me, feed me, feed me. So I'm trying to be the mother hen with them under my wings. Then something I baked, and that is a drawing I did of my grandmother. So that's about me. Let me see how the time's going well. So now I'm going to tell you a little bit about computation and density functional theory. So as I said in my abstract, materials are so fundamental and central to our lives that we actually measure the progress of human civilization by what material is used, what new material is used at that time. So we first had the Stone Age, then we had the Copper Age, then we had the Bronze Age, and then we had the Iron Age. For me, the most fascinating of these is the Bronze Age. Can anyone guess why I'm particularly fascinated by the Bronze Age as opposed to any of the others? Yes. Huh? I can't make out what is, huh? Indus Valley civilization certainly did use bronze. For example, the famous dancing girl of Mohenjo-daro is made of bronze. But as a material scientist, why do you think bronze would be especially fascinating? Huh? Yeah, they mix things. So okay, one shouldn't use these expressions like man-made anymore because they're gendered, but they're made by humans. It doesn't exist in nature. Whereas stone, copper, iron do exist. But bronze is an alloy of copper and tin. And if you make it, it has superior qualities. And it's fascinating to think about how all that long ago, somehow people realized that if you mix these two materials, you can get something with superior qualities. Okay. And this thing, my students told me to add this because this is supposed to be a joke about the Iron Age. And they said, if we don't put this, nobody will notice it. Okay. So this is, of course, the periodic table. And there are 98 naturally occurring elements. And there are about 4,000 naturally occurring minerals. But the whole point is that we can design new materials. So this is the periodic table. It's like assembled out of Lego blocks to show that the elements are like Lego blocks for us. We can put them together in various combinations to make new materials. And that's sort of what materials science or condensed matter physics is all about. So how many can you make? So before the advent of the internet, there used to be these books called the Landau-Bernstein books, which had lists of all the materials people had made, okay? And there would be shelf after shelf in a library. Now, of course, it's all online. But people have sort of tried to estimate how many can be made and be stable. And they think that if you make a quaternary compound, that is with 4 elements in it, you would get of the order of 10 raised to 11 possibilities. And if you make quinary, that is with 5, then it goes up to about 10 to the 13. Now that's just huge. Now, how do you search in this space? How do you know? Sure.
Why is it finite, the number?
So there's some rules about what mixes with what. So this is just an estimate. I mean, there are rules. I'll talk about one rule later not everything will mix with everything. There are rules that depend on this difference in sizes, the difference in electronegativity, etc. So that is what reduces the number of possibilities. So, and yeah, in principle, of course, it's infinite. And I mean, you can also go to larger and larger unit cells. So they're making some assumption here, I think, about all already known crystal structures and assuming that it's not some completely unknown crystal structure, etc. Yeah, so I think they accounted for some range of temperature and some range of pressure, but not a huge range of pressure. So people, how did material scientists work? Okay, they either found things by accident or they found them out by trial and error. Like just try hundreds of things, thousands of things. So a famous example is the Haber process, which is the synthesis of ammonia from nitrogen and hydrogen, for which you need a catalyst. So what catalyst can you use? So when they first developed this process, they tried about 2,500 materials. Okay. Now we use iron. They decided iron was the best. Actually, iron wasn't the best of what they tested. Osmium was the best, but that osmium is very rare. There was very little osmium available worldwide, and so it doesn't make sense to use it for an industrial process. So they decided of the 2,500 things they tested, iron is the best. It is still the most commonly used today, but by now it's been estimated that about 250,000 materials have been tested as the catalyst for the Haber process. But this isn't necessarily an efficient way of going about it. It's not also very intellectually satisfying. So what people want to do now is replace this trial and error or brute force method with what's called rational materials design, okay, which requires a to and fro between theory and experiment. So now let me, since I had given the title as why do computation, let me talk a little bit about theory and experiment. Now, I'm going to ask the students here, how many of you prefer theory? Very few. And how many prefer experiment? Okay, mostly experiment. So let's see if I can change your mind. So, so it's traditional that there is some kind of banter between theorists and experimentalists. So in this cartoon, you're saying, a theorist is saying, you experimentalists are inferior, you're just a bunch of stamp collectors. And the experimentalist is saying, what do theorists do? That's so great. And so I collected a couple of quotations. So here is Leon Lederman, who the particle physicists will know. I guess he was the director of Fermilab. So he says, a theoretical physicist can spend his entire lifetime missing the intellectual challenge of experimental work. So I highlighted that because theorists will claim that there is no intellectual challenge in experimental work. Experiencing none of the thrills and dangers, the overhead crane with its 10-ton load, the flashing skull and crossbones and danger, radioactivity science, a theorist's only real hazard is stabbing himself with a pencil while attacking a bug that crawls out of his calculations. So I like that phrase a lot, even though I'm a theorist. Okay, and this theorist, this experimentalist, I suppose most of you know who this is. This is Sheldon Cooper, and he really looks down on experimentalists. Now, recently, I came across a very interesting example of this theorist versus experimental debate, and so I will share that with you. There's this book, okay, which came out about a year or two ago. It's a bestseller. Really, it is. Like, I visited the US last year and it was on all the bookstores, all the shelves. It's called Love Theoretically. It's this genre of literature which is disparagingly called chick lit. Okay. It's not a very good book, I'm telling you. But it's a lot of fun to read, especially for a physicist like me. And to give you an idea of what the book's theme is, I put things. Okay, so this is from the blurb, the first sentence. It says, Jack Smith, the annoyingly attractive and arrogant elder brother of her favorite client. So the heroine is a theoretical physicist. Don't ask me why a theoretical physicist has a client. That's another whole other story. Okay. Turns out to be the cold-hearted experimental physicist who undermined the reputation of theorists everywhere. And he's the same Jack Smith who rules over the physics department at MIT. And then, of course, will falling into an experimentalist orbit finally tempt her to put her most guarded theories on love into practice. Okay. Okay, so now I come to why do computations. So nowadays, increasingly, computations are often beginning to replace experiments because they are cheaper. I said can work from home, partly as a joke, but also because it's really true. It can often be an advantage. Believe me, during the pandemic times, we really appreciated that we could work from home. But also, for example, one of the postdocs I had, she actually switched from experiment to computation because she had 2 young children and she found it very hard to spare the time to do the lab work, whereas she could do her calculations from home. It's often a lot quicker, most of the time, to do the computation than to do the experiment. It can lead to greater understanding. It can simulate conditions that can be very difficult to achieve in the lab. So, for example, if you want to know what exactly is happening to the iron at the center of the Earth's core, or what is happening at the center of Jupiter, I mean, these are such high temperatures, high pressures, etc., that it's very hard to do that experiment. But on your computer, it isn't really that much more difficult to do a high pressure than a low pressure. So in such situations, computation is often your only recourse. I said you can switch off effects such as relativities and pressure, magnetism, etc. So for example, I want to know, I'm seeing some property of a material. I want to know, is that because of relativity or not? So I can do the calculation relativistically and non-relativistically and see if I get that property or not. In an experiment, you can't really do that. Okay, so this is an advantage. And we can make predictions for experimentalists to verify. I thought I had another slide here. Okay, so let me go back a bit. I thought I don't know. Okay, that slide seems to have disappeared. So let me tell you what is the basic problem we're trying to solve in condensed matter physics or in material science or in atomic physics even. So you basically have a many-body system. So you have some number of nuclei, some number of electrons. They interact by the Coulomb interaction. So examples are atoms, molecules, condensed matter systems. And we know how to write down the equation that governs the properties of the system. It's the many-body Schrödinger equation. Okay, so it's H psi equals E psi, where psi is a many-body wave function. The H will have the kinetic energy of the electrons, the kinetic energy of the nuclei, and then 3 types of Coulomb interaction terms between nuclei, between electrons, and between nuclei and electrons. So writing the equation is not a problem. Okay, and then of course you have to do things like satisfy Pauli exclusion principle. But it is basically impossible to solve this, or at least very, very difficult to solve it. So here is a quote, a very famous quote from Dirac. And he said, the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known, and the difficulty is only that the exact application of these laws leads to equations much too complicated to be soluble. Okay, so we can write the equation, but we can't solve it. So how do you solve the many-body problem? One approach is to use density functional theory, which people usually refer to as DFT. So what you do in DFT is you map this many electron problem onto a one-body problem. So I have an analogy for this. It might seem a bit silly, but it is still informative, I believe. So supposing you have a many-person system like this, okay? So if you want, you can think of the blue guys as nuclei and the red women as electrons, okay? And they have complicated interactions between them. And the problem I've given you, the goal is to arrange them all so that you reach the optimal level of happiness. Global happiness is greatest. In your nuclei and electron problem, you have to arrange them so that the total energy of the system is lowest. This is clearly a hard problem to solve. What you do in density functional theory is you map it on into a system where you have these guys and you have only one woman and you have to decide where to put her. Okay? Which is clearly an easier problem to solve. But the remarkable thing is that there is an exact mapping of this sort, such that the solution to the problem on the right is exactly the same as the solution to the problem on the left. But you have to pay some price for this, which is that your Hamiltonian now changes. Okay, so to symbolically show that, I've put these face masks on these guys to show that the interactions are now different. And if you got the right face mask, the solution would be exactly the same. The problem is that this theorem, that the mapping is exact, is an existence proof. It tells you there exists such a mapping, but we don't know what the mapping is. Okay, but we have very, very good guesses for it, which is why we use it. But people are still trying to find that exact mapping. So that's a challenge for your generation. If you can find that exact mapping, you will surely get a Nobel Prize. Okay? So the person who developed density functional theory is Walter Kohn. He has a very interesting and very inspiring personal story. I won't go into it here for lack of time, but do go and look it up. Okay? And he got the Nobel Prize in 1998 for developing this method. Okay? So DFT calculations are also often called first principles calculations or ab initio calculations. And the reason for that is that the only input from experiment is atomic numbers and atomic masses. And then you just churn through the machinery of DFT, and then you get remarkably accurate output of lots of things, of which I'll show you some examples. Okay, so before DFT was developed, what you did when you did calculations of this sort was you would take some empirical or experimental observation and using that try to calculate some other property. Like if you knew the if you knew the bulk modulus of a material, you would try to calculate the phonon frequencies of that material or something like that. But here we don't do that. There's no experimental input whatsoever except for atomic masses and atomic numbers. Okay, so here's the, so how do we do this? How do we now design materials? You take some materials, material A, material B, material C, you do your DFT computations, you analyze your results, then using that you obtain some insight into design principles, which is the hard part, and then using this insight, you can design a new material with desired properties. Do you know where I've taken these pictures from? Does anybody know? No? Yes. So PhD Comics is a very nice comic strip about what it's like to be a PhD student in science, but it's also just in general nice about science. So if you haven't read it, it's available online, just go look at it. Okay, so fine, still on schedule. So now I'll give you some examples of work from my group. I'm just going to give you a rather superficial look at the work. I can't go into all the details, but I just want to give you a flavor for the kind of problems we look at. And then if you're more interested, of course, you can read the papers or you can contact me or whatever. Okay, so I'll give some examples from our work over the past decade of how we use DFT to understand the properties. So in our group, we do some bulk materials, but we mostly specialize in nanomaterials. Our group is called the Computational Nanoscience Group, and we design new materials. Okay, so the first question is what I already alluded to, which is, can we make a new material? And in particular, can we design a new alloy? So with reference to the question Professor Bengaluru asked, can you just mix any two metals and get an alloy? And the answer is no. Only some metals will mix with others. And there are a set of rules called the Hume-Rothery rules, which tell you when you can mix them to make an alloy. And I'm only mentioning one of those rules here, which is the simplest one to visualize, which says that if you have two metals, you have a metal A, which has rather small atoms, and a metal B, which has rather large atoms. If the difference in size is more than 15%, then you cannot make an alloy out of A and B. So people were trying to think, is there some way to get around this constraint? And one thing that people came up with, one idea, was what's called a surface alloy. That is, if you have these orange atoms and blue atoms, which differ in size, what if you put just one layer of them, which is something we can do experimentally, on a substrate where the atoms have intermediate size? Okay, this is what's called a strain stabilized surface alloy. So they tried to make this. In some cases, it worked, but in many cases, it didn't work. And experimentalists were spending a lot of time trying to make them and failing. So there's this experimental group in Paris, headed by a scientist called Sylvie Rousset. And she approached me and asked if our group could help her design a system where they would succeed in this. And I'm skipping the details of how we narrowed the possibilities down, but the calculations were done by my student Madhura Marathe, and she said if you take iron and gold, now iron and gold basically don't mix in the bulk, but she said if you take iron and gold and deposit just one layer of them on a substrate of ruthenium, then it will form a surface alloy. And these are what are called scanning tunneling microscope images. I hope you know what they are, STM. So on the left is the experimental STM image. On the right is the theoretical STM image. So each of those black circles is an iron atom, a single iron atom. And each of those white dots is a single gold atom. So it forms an alloy with this particular structure, where every iron atom is surrounded by 6 gold atoms. Okay. Now, the interesting thing is, though we thought that this system would form a surface alloy, this particular structure was something we hadn't tested. We hadn't realized this would be the ground state structure. We had tested some other structure. So after they showed us these experimental results, we went back and calculated a bunch of other structures. I won't go into the details of what this plot shows. It's something called heat of formation or enthalpy of formation. And the important thing is just that the most likely structure to occur is what's circled in pink. And that structure corresponds to the one that's observed experimentally. So experiments and calculations agree about what is the most likely structure. Then the question is, why? Why is it that structure out of all those that forms? And why does it form? And this was again a real surprise, which you could only get out of the calculation, and it was a very unexpected answer. And we found that the formation of the alloy is stabilized by magnetism. So you know that iron is ferromagnetic. Now it turns out that in this particular structure, where every iron atom is surrounded by 6 gold atoms, the iron atoms acquire a very high magnetic moment. And then that lowers the energy of the system considerably, and that is why the alloy forms and why it forms in this structure. So this is an example of going back and forth, theory, calculations, experiment, and then making a new material. So I'll now go to another example. So the next few examples I'll show you are on supported metal nanoparticles. So why are they important? I'll give you an example. This is a catalytic converter. Okay, so this is a part of every car, unless it's an electric car. So in this catalytic converter, there is a ceramic oxide, and on it are little metal nanoparticles. And these metal nanoparticles are catalysts, and they do things like, for example, when you combust your fuel, you produce carbon monoxide, and that's of course really poisonous. So you have to oxidize it to carbon dioxide before you let it out into the atmosphere. Carbon dioxide is also, of course, not good, but at least it's better than carbon monoxide. Okay, so for these reasons, one wants to study systems like this. So the first question here, which we asked, is whether we can change the shape of the nanoparticle. Okay, so here, so if you put, okay, there's another whole weird thing there, which is that you use gold often, and I'm not going to why, but here, if you put a nanoparticle of gold on, for example, an MgO surface, it forms this clumped up structure. In this particular case, it's formed this tetrahedral pyramidal structure. But what one would prefer is that it form such a flat planar structure, because you believe that it will be a better catalyst. And the question is, how do you make it change the shape? And our theoretical idea was that if you do what's called support doping, so in this oxide, these gray atoms are magnesium atoms, and here you replace some of these magnesium atoms with these purple aluminum atoms, then the shape will just naturally change. Okay, and this calculation was done by my student Nisha, and this is a very special picture, because if you've been looking at a picture very carefully, you will notice that her earrings, one of them is the planar nanoparticle and one is the tetrahedral nanoparticle. So, and why this happens, why does this change in shape happen, is that there's a change. This is again something we can see from our calculations. So what is shown in red and blue here is a gain in electrons is shown in red and a loss in electrons is shown in blue. And basically what happens is that when you put these aluminum atoms, they donate electrons to the system. These are transferred to the gold, and then the gold prefers to flatten out for electrostatic energy reasons. Okay, so then, okay, does this really work? So someone did the experiments just a few months after our paper. This was a group of someone called Freund in Berlin. They didn't do it on exactly the same system, slightly different. Instead of MgO, they used calcium oxide. Instead of aluminum dopant, they used molybdenum dopant, but it's exactly the same idea. So this is the STM image of it on the undoped oxide. So you see that the nanoparticles are clumped up. And then when they put it on the doped oxide, you see they're flat. They're just one atomic layer thin. They're like chapatis. Okay? So this is very exciting as a theorist, that you predict something and someone does the experiment and it works. Okay? Now, just to temper it with some negative stuff, we also predicted that it would be a very good catalyst, because that's why we were doing it. Okay, so this is again from density functional theory. What we're doing here is on this flat gold nanoparticle, we are putting in blue here an oxygen molecule, and we're stretching the molecule till it breaks. So we're dissociating the oxygen. And what these green dots here are showing you is how the energy changes when you do that. Okay? And we find that if you look at that energy, the energy it requires to dissociate it, when you have the undoped support and the clumped up nanoparticle, it's 0.68 eV. If you do this instead, it lowers significantly to 0.29 eV. So that means the reaction is much easier to take place. Now, the sad thing, however, is that many people have been trying to reproduce this experimentally, and they haven't yet succeeded. We have some ideas about why it's not succeeding. We think it's because there are defects in the oxide which are trapping the electrons, etc. So now we have to again think, how can we now make it happen? Okay, the third example is, okay, so now we have these small nanoparticles. This is okay, let me see. Okay, what you should look at, I'm going to start a video in a moment. This is an electron micrograph. What you're seeing here are pictures. Each of these is a gold nanoparticle, and it's on an oxide support. And you're going to see them moving just because of temperature effects. And what you will see is that these two will move and join up, and then these two will move and then join up. So let me start the video. Okay, so you saw those two move and join up. And then if I run the video long enough, you will see another two move and join up. So this process is called sintering. Okay, and it's something we don't want at all. Okay, why don't we want it? So if you look, for example, at this reaction of carbon monoxide oxidation, and you see how well it proceeds versus the diameter of the gold particles, you see it, as the particle diameter becomes smaller and smaller, it's faster and faster. So you really want your gold nanoparticles to be small. You don't want them to join together and form bigger and bigger nanoparticles. But this is what happens in practice. So this sintering is the biggest cause of catalyst degradation. It spoils your catalyst. So we wanted to study, how do these particles move? How do they join up? Are all metals equally likely to do this? That kind of thing. So what kind of sizes should we study? Nowadays, people are actually interested in single atom catalysts. So your catalyst is just one atom of the metal. So I've just shown you here one picture from the literature. This blue atom is a single platinum atom on ceria. And it's a good catalyst for this reaction where methanol is converted to carbon monoxide and hydrogen. Why is this? You may think this is backwards of what you want, but it's a way, like if you want to have a hydrogen-powered vehicle, you don't want to carry along big tanks full of hydrogen because they're very big and dangerous. So the idea here is that you carry along methanol, and then when you need hydrogen to fuel your car, you perform this reaction and you get the hydrogen. Okay, so the first thing we did was we put a single platinum atom on an MgO surface and we checked how it moved. And you see it moves as one would expect by process of hopping. This lower graph here shows you how the energy changes along the process. So this height here is the barrier, the diffusion barrier, the energy you have to supply for the atom to move. Okay, nothing too exciting here. The first surprise comes when you look at two atoms, a dimer, a nanoparticle formed of two atoms. And what you see is that it doesn't just translate along. It does this cartwheeling motion. Okay? And the barrier is significantly lowered. Now, if you look at the trimer, which is a particle composed of 3 atoms of platinum, it does yet a different kind of motion. It kind of walks along. And when I saw it, I said, I've seen something that moves like this. And then I finally remembered it was this. Do you know what's that picture on the right, where it's from? You're all too young, mostly. Any old people in the audience know what this is? Yeah, Star Wars. It's called an AT-AT walker. Okay. And then if you look at 4 atoms, then it does yet another motion. It rolls along. Okay. So the first surprise was the ways these things moved. And then we also found this strange relation, which is that the diffusion barriers for different metals scaled with the bulk melting temperature. Okay, except for dimers. So now I want to explain to you what a surprising result this is. You have one atom of a metal and it's going to move along a surface. But the energy it takes for that to happen is proportional for the bulk of that metal to melt, the temperature. And this is actually, I mean, initially when we said this, the referees just howled in outrage and said it's impossible and this cannot be, this is an accident and all that. But we actually worked it all through step by step and showed where this relation arises from. And this gives you a very simple rule of thumb. If you do not want your nanoparticles to sinter, use a metal which has a high melting temperature. Okay. And then from this, we can also study the processes by which this sintering happens, because we have the diffusion barriers, etc. And we find the process is different for different metals. I'll just show you this one, okay? We find that if you want to take 4 platinum atoms, okay, single atoms, and then sinter them into a tetramer for 4-atom nanoparticle, it happens with addition of 1 atom at a time. It's called monomer addition, which is what you'd expect. But people always thought monomer addition means you have a larger nanoparticle, 1 atom diffuses along, comes and joins it. But what we found is the opposite's happening. The 1 atom is staying stationary and the larger nanoparticle is moving and joining it. Okay, so the last example I have is we're starting to look at what are called molecular machines. So this is an example of a molecular rotor. So it's a molecule which is moving. So in collaboration with an experimental group in Germany, we're looking at some of these systems. So what's there is again a scanning tunneling micrograph. Okay, so can you see that the silver things are moving? They're actually rotating, but sort of in a punctuated way. They're switching. Okay, so this is my student Abhishek, and what is there is his theoretical simulation obtained from DFT. So he has the same molecules, And what is in yellow and green are again electron gain and electron loss. And when you have one of these lines of alternating yellow and green, that is a hydrogen bond formed between the central rotor and the cage it's rotating in. And here, what is shown here is as the position changes, he can compute the energy of the system. Okay, and what we find is that when there are a lot of these hydrogen bonds, the energy is low. And when there are very few of these hydrogen bonds, the energy is high. Okay, this seems very obvious, but it was the first time someone had shown it. And we can also calculate the barrier for this rotation. And that's also something they can measure experimentally by doing experiments where they change the temperature. And the agreement was sort of embarrassingly good because you don't normally expect such good agreement between calculation and experiment. So we got 0.944 EV and the experiment said 0.95 plus or minus 0.07. Okay, so let's see. Okay, I think I'm done. So first principles techniques, what I want to tell you is can be used successfully for the computational design of novel materials and can provide insight into why materials have the properties that they do. I do have to tell you that DFT is limited always by what the available hardware can do, but of course hardware keeps changing all the time. So right now we can simulate systems with about thousands of atoms. If you want to simulate dynamics, then we can simulate about 1 femtosecond, which is very short. And I haven't discussed at all machine learning, which is the latest thing that's transforming our field. And the next thing that people are beginning to work on is how quantum computation is going to change the field, one hopes. Okay, so that's all I have to say. Thank you.
Thank you, Shobhana, for really a very wonderful lecture. It was nice that you shared some of your story and very nicely told too, and a wonderful lecture about the DFT and how to make new materials. We are, of course, very happy that one of the Vidushis in your group. Questions? Please feel free to ask any questions you like. Yeah, don't hesitate.
So you spoke about nanoparticles on a substrate, a single layer. So why is it that the bigger nanoparticles move towards the smaller nanoparticles? It should be the reverse, right?
Yeah, so that is just a peculiarity of platinum. The platinum monomer requires a lot of energy to move for a reason that I still do not understand. For gold, this is not true. The opposite is true. And for platinum also, I would expect that some much larger size this behavior would change. Like I would expect if you had a really large nanoparticle, then it would start costing more energy to move the large particle than the monomer. But at the small sizes we saw, this is what we found.
Good afternoon, ma'am. So I just wanted to ask, like you, in the examples that you showed us, you've used gold as often. You have used that often. So I just wanted to ask, what is so special about gold that you are using it in most of the examples that you've shown?
Yeah, so this was actually a real surprise in the field. So as you know, we use gold for jewelry. So why is it that we value gold? One of the reasons I think we value gold is that it is very unreactive. Okay. So for example, if you have silver jewelry, it tarnishes because it becomes black because it oxidizes. Gold is very unreactive. It does not react easily, it does not oxidize easily, etc. But a real surprise in the field that came about 30, 40 years ago was people found that if you have gold nanoparticles, this is not true. Okay. Gold nanoparticles are very reactive.
Okay.
and they become very good catalysts. It's a bit technical why that happens. And according to me, it is still an open question why they are good nanocatalysts. Like, I mean, there's a standard explanation in the field, which I don't find completely convincing. Yeah, I think it's too hard to explain in simple words. But if you're interested in it, if you write to me, I'll send you some papers.
Okay. And I also wanted to ask, like, if one, we have not read about DFT yet. So if one wants to start reading about DFT and studying about it, so from where should we start?
Okay, so I'm going to be biased and tell you that the easiest introduction is, do you know resonance?
Yes.
So in resonance, some years ago, I wrote 2 articles. Okay, it's such a stupid title. I'm a bit embarrassed to tell you. It's called Hum Kaun Hai because it's Kohn,
Okay.
Walter Kohn who did it. So if you look for that, and then there's another one about Walter Kohn, his biography. I think those might be good places to start because it's more technical than what I told you. It has some of the equations and things like that.
Okay, thank you.
So has it ever happened that you did your computation for maybe 4 months, 5 months, got some nice result, and then you realize, oh, I could have guessed it theoretically anyway. I didn't need to do these 4 months of calculations.
Not really. What is happens much more often is that we do the computation and then the result doesn't agree with the experiment. I've only shown you the success stories except for the catalytic activity. I mean, it's not so simple as I showed. It's not just that you put in the input and turn the crank and the result spits out. There's much more sophistication and complexity to it, and there are various effects you have to take into account. And the ultimate test is always experiment. And it doesn't matter how beautiful a calculation you do if it doesn't agree with the experiment. I don't think I've ever encountered a case where I just felt that I could have guessed the result all along. But maybe I'm just not smart enough to do that.
Let me ask the opposite question. Has it ever happened that your calculations gave you a result and you just said this simply cannot happen with normal input?
I have
complete
felt that.
counterintuitive result.
I have not felt that, but the referees have often felt that.
Anyone else?
Ma'am, you showed us an analogy of the boys wearing a mask after the process was made. So I just wanted to ask if you're trying to make a reference to the pseudo potentials that we use in DFT.
No, it's not the pseudo potentials, it's the exchange correlation functional. And I realize it's not a very good analogy because your question is, of course, right, because what the nuclei wear is the pseudo potential. And therefore, the analogy should be more to the pseudo potential than the exchange correlation functional. But I didn't quite know how to make an analogy to the exchange correlation functional. So that's why I put the mask. Also, the first time I made this slide was during COVID time. So the mask came naturally.
Thank you.
Anyone else? Then I
have a quick question.
Yeah, go ahead.
So from your slide presentation, which of course was wonderful, what is the driving force? Are you looking for catalytic converters for green energy or improve the energy things and all? What will be the commercial visualization for this kind of research? I mean, finding a new element sounds good, but then there has to be some reason for doing this.
For example, we can try to find better catalysts, better magnets. Those are 2 immediate examples that come to mind. We are also now trying to design, for example, materials for qubits, etc. So some property that has to be optimized. Now, for the catalyst, for example, when you say I want to make a better catalyst, it could be that it should be a faster catalyst. It could be one that works at a lower temperature. It could be one that is cheaper. Now, when you say it is cheaper, there are two ways a catalyst could be cheaper. It could be that it uses less amount of a more expensive material. So, for example, a nanoparticle is that. A nanoparticle is also often just faster, better. Or it could be just that it uses a less expensive element. So, for example, the catalytic converters in cars, they use platinum, palladium, and rhodium, all of which are extremely expensive. Most of the time, all three are more expensive than gold. Right now, rhodium is way more expensive than gold. So you don't want to use these. So you're trying to find other elements that you can use instead of them so that you don't have to use these expensive materials.
So I know you didn't talk about machine learning, but I just wanted to ask you that in which part of the work you think the machine learning will make a maximum impact?
Okay, so machine learning is completely transforming all parts of density functional theory. So one thing is that, you know, when you have to try to find a new material and you don't know what property of the material you have to optimize at the microscopic level to get the property you want, then you do a lot of DFT calculations. You correlate it with the property and the machine learns from the database and then designs a material which will give you the property or finds the descriptor for you. So that's one thing. Another thing is if you want to do a calculation on a huge system, or if you want to run a simulation for a very long time, it's computationally expensive. So you, instead of doing full-fledged DFT, you develop what are called machine learned potentials, which are model potentials, but obtained from machine learning, which you can then use. And with these potentials, it's much cheaper to do the calculation. But because they've been developed with machine learning, they're supposed to give you the DFT accuracy. And I would say the third area where they're used is, I told you, we don't know this mask, or as I told her, the exchange correlation functional. And people are now using machine learning to try to learn what this exchange correlation functional is. So these are the three main areas, I would say. Thank you.
The questions? I request everybody to appreciate the wonderful speak which we got and the things. I also invite everybody to have a tea near the
Thanks, and please write to me or write to Garima if you have any questions or are interested in our work.
Invite her next week.
Okay.
I will definitely, of course, we can write, but that's very wonderfully